think back to your high school math class,
Yeah.
right? Um, if you are like most people, you probably pictured math as this cold, towering monument of absolute truth.
Oh, absolutely. Just completely rigid.
Right. You sit down, you open a textbook, and you were taught that a formula is just, well, it's just a formula, existing entirely outside of human
Yeah,
experience.
in a vacuum.
Exactly. You were told it's a universal language, that finding the area of a triangle is exactly the same sterile process, whether you are sitting in a classroom in New York or, a laboratory in Tokyo.
Right.
But what if that rigid, completely culture-free version of math is actually a myth? And worse, what if teaching it that way is completely failing to prepare us for the real world?
I mean, it is a profound myth, and it's one we really need to dismantle. We have this tendency to treat mathematics as if it were handed down from the cosmos,
Right.
completely detached from the messy realities of human life, culture, and, well, daily work. But when you look at the shifting landscape of our global economy, that rigid definition is cracking. It just doesn't hold up anymore.
And that is exactly what we are getting into today on this deep dive. We've got this fascinating stack of research in front of us from the CIEAEM 65 conference in Turin.
Yeah, really incredible gathering.
It really was. And they focused on mathematics education in a globalized environment. The core argument here flips everything we hated about high school math completely on its head.
It really does.
We are exploring how globalization, diverse cultures, and the actual reality of modern workplaces are forcing us to radically redefine what math is, how it should be taught, and why that actually matters to you.
Because if we look at the broader context, borders are blurring and information is moving faster than ever. The traditional model of education, where you go to school, memorize a set of static facts, and apply those exact same facts to a single lifelong job,
Yeah, that's just gone.
it is completely obsolete. Today, workers constantly have to learn systems that do not currently exist. Memorizing a static formula for a test doesn't prepare you for a world that demands continuous, dynamic problem solving.
Okay, let's unpack this, because before we can talk about fixing how we teach math, we have to look at where the current textbook version is actively failing.
Right.
There is this massive disconnect between the classroom and the factory floor. The research challenges the old UNESCO assumption that math is just pure universal abstraction. Instead, researcher Franco Favilli argues that math actually stems from deeply cultural human activities.
Yes, 6 specific ones, actually.
Right. Counting, locating, measuring, designing, playing, and explaining.
Exactly. Those activities are universal human behaviors, but how they manifest depends entirely on the context. If you ignore the context and just teach the abstraction, you end up teaching a version of math that is effectively useless in practice.
There is a brilliant, almost hilarious example of this from researcher Gail Fitzsimons. She highlights a pharmaceutical training manual.
Oh, this one is unbelievable.
It really is. Imagine you are a worker standing on a highly regulated, sterile factory floor. A machine breaks down at noon, and it starts up again at 1:05 p.m. The training manual literally asks the worker, what is the probability of a breakdown on the stroke of 12 noon?
Which is a completely absurd question for someone in that environment to answer.
It makes no sense. If you are working on a pharmaceutical line, you do not care about the abstract mathematical probability of the clock striking exactly 12.
No, you care about sanitation.
Exactly. Sanitation line clearances, which specific part broke, preventing a massive contamination issue. The textbook math problem completely ignores the reality of the worker's environment.
And completely detached.
There's another great example in the sources about electricians. They sit in a classroom learning formal trigonometry, sketching out complex angles and sine waves. But on the job site, they bypass formal trig entirely.
Because they have specialized tools.
Right. Tools that have the calculations physically inscribed on them to do the conduit bending work for them. Teaching abstract trigonometry to that electrician is like teaching someone the complex physics of gyroscopic motion just so they can ride a bicycle to work.
That's a great analogy.
It entirely misses the practical application.
And this highlights the core problem. The global economy demands workers who can blend theoretical knowledge with what we call tacit or cultural knowledge.
Tacit knowledge, right.
Yeah, a standard multiple choice test might tell you if an electrician can memorize an equation, but it completely fails to measure the dynamic, situational problem solving they actually use when their hands are on the tools.
So if the textbook math is failing the worker, what does real working math look like? To answer that, The research takes us away from the factory floor and out into the agricultural fields of France to look at the French vine pruner.
This is such a fascinating shift because researcher Gerard Verneau provides a brilliant way to categorize this disconnect. Think about the difference between what you can write down in an equation, which we can call predicative knowledge,
Okay, predicative knowledge.
and what you actually do with your hands and your brain in the moment, which is operative knowledge. The mind pruner, the Théodovine, is the ultimate embodiment of operative knowledge.
Right, because a single pruner might cut up to 800 vines in a single day.
Yeah.
And they're making these rapid-fire, highly complex geometric and biological calculations without ever pausing to pull out a notepad.
Never.
They rely on what they call pragmatic concepts. They look at the vine and assess its charge, meaning its load and its equilibria, its balance. In a split second, they are looking at the shape of the wood and anticipating how the sap is going to flow and how that plant will grow 3 years into the future.
It is incredibly complex spatial reasoning.
But, and here's my pushback, I struggle with calling that math, though.
Why is that?
Well, if I am in the outfield and I catch a fly baseball, my brain is technically calculating a complex parabolic trajectory based on wind speed and gravity.
Sure.
But I'm not doing math, I'm just playing a sport.
Yeah.
It's muscle memory. How is the vine pruner any different than just agricultural intuition?
What's fascinating here is that the distinction between reflex and operative knowledge is vital. If you catch a baseball, you are reacting. But the vine pruner isn't just reacting to gravity.
Okay.
They are operating within a functional framework that Verneau calls a schema.
A schema.
Yes, a dynamic organization of activity. A schema involves specific goals, conscious rules of action, and invariance, meaning they are actively applying a set of rules to different variables. They aren't just letting muscle memory take over.
Oh, I see.
They are consciously engaged in spatial reasoning, geometry, and predictive modeling. It absolutely is high-level math. It's just happening in a highly specialized, non-written form. The mathematics is embedded directly in the action.
Okay, that actually changes things. Because if we admit that a vine pruner working in a field is doing valid high-level math without a textbook, we also have to admit that formal Western classrooms don't hold monopoly on mathematics.
Exactly.
Which forces us to look at indigenous cultures and brings us to the concept of ethnomathematics.
Ethnomathematics is a crucial shift in perspective. It moves us away from the colonial idea that academic math is the only valid system. When you look closely at diverse cultures, you find highly advanced, localized mathematical systems everywhere.
Right.
And bringing that indigenous knowledge into the classroom, validating those systems, grants those cultures dignity in a globalized space.
The examples here in Favilli's research are amazing. Take the traditional Andean pipes, the zampoña. The artisans who build these instruments don't use standard mass-produced rulers with inches or centimeters.
Right. They use their own systems.
Yeah, they use a wooden strip with notches based entirely on their own experiential scale. And yet they achieve mathematically perfect musical notes. They have a deeply personal cultural measurement system.
And we see similarly complex structures in storytelling. In Angola and parts of India, storytellers create intricate patterns in the sand known as sona drawings to accompany their oral histories.
These are incredible to look at.
They really are. They draw a grid of dots in the sand and then trace continuous lines around them.
And the mechanics of how they do this are just staggering. So imagine a grid of dots in the sand, let's say 4 dots wide by 6 dots long. The storyteller puts their finger in the sand and starts dragging it in a diagonal loop, weaving between the dots and bouncing off the imaginary edge of the grid like a pong ball.
Right.
They keep going until the line loops back to where it started. But here's the crazy part. If that single loop didn't enclose every single dot on the grid perfectly, they start a second loop.
Yes.
And if you map it out mathematically, the number of separate continuous loops they have to draw to enclose every dot perfectly matches the greatest common divisor of the grid's dimensions.
Exactly. So for a 4x6 grid, the greatest common divisor is 2.
Right. So it takes exactly 2 loops to complete the drawing. They aren't writing down fractions or doing long division on a chalkboard, but they are physically executing a complex mathematical algorithm just by passing down their cultural narratives in the sand.
Which completely reframes who we even consider a mathematician. And perhaps one of the most striking cultural tools we see is the ancient Inca abacus, the Yupana.
Here's where it gets really interesting. The Spanish conquistadors destroyed most of the physical heritage of the Inca, but we still have drawings of the Yupana.
Thankfully.
Yeah, and researchers recently translated the logic of this ancient board into a modern computer drag-and-drop format for students because it doesn't work like the math we write on paper.
No, it works to positional arithmetic.
Exactly. Imagine a grid board. Instead of writing out the equation 9 plus 2, you have 9 small stones in the ones column of the board. You need to add 2. But the physical rule of the board dictates that a column can only ever hold 9 stones. So instead of trying to conceptualize the abstract number 11, you physically pick up 10 stones, move your hand over to the next column, and drop 1 stone in the 10 space. You just executed a base change visually and physically.
It's brilliant.
When you look at the physical positional logic of the Yupana, it feels exactly like early computer programming. You are just moving data blocks around a grid based on hard rules.
Yeah.
These ancient tools were actually incredibly modern in their functional logic.
It is incredibly modern. But if we recognize that math is this diverse, localized, cultural tool, we have to rethink the modern classroom. You can't just have a strict lecturer handing down rigid formulas anymore. The role of the teacher has to fundamentally change.
Right, because as researcher Nuria Gorgoria points out, globalization brings massive transitions. You have immigrant students coming into new countries facing huge cultural ruptures in their lives.
Absolutely. Displacement is a major factor.
They are sitting in a classroom where the cultural norms are completely foreign to them. Gregorio suggests that the math teacher actually becomes this vital social resource, helping students construct new mathematical identities while navigating this new foreign classroom culture.
And researchers Applebaum and Gorofsky take this concept even further, bridging it into the realm of civic action. If mathematics is a local cultural tool, then it can be used by communities to advocate for themselves.
Okay.
Now, to be clear, we are just imparting what the research says here, but they tie this into a movement called alter-globalization.
Alter-globalization. So instead of anti-globalization, it's an alternative.
Precisely. It's a movement that doesn't reject global connection, but it pushes back against corporate homogenization. It seeks to preserve cultural diversity and local identity. The participants advocate for participatory citizenship, often combining math with performance art to claim public spaces.
Right, the research mentions these fascinating civic actions, like the Orange Alternative in Poland in the 1980s, where citizens peacefully mocked the authoritarian regime by dressing up as gnomes, or the Spiral Q puppet parades in Philadelphia, which are used to build community organization.
And Applebaum and Jarofsky actually propose bringing the spirit into mathematics, creating something they call a math-aquatics squad.
Okay, so what does this all mean? How do we get from a French mind pruner doing field math to a nomadic math squad leading puppet parades? Are we seriously expecting math teachers to become avant-garde performance artists and community organizers? How do you even grade a math-based puppet parade?
This raises an important question, and it sounds like a massive leap, but the logic is actually very practical. If math is a tool for understanding the world, then students should use it to interact with their community.
Give me an example.
Imagine a neighborhood that desperately needs a new stoplight. Instead of just complaining, the Mathquatics squad students and teachers, acting as co-learners, goes out, gathers the traffic data, builds the statistical models, and proves the danger mathematically.
Okay, I track that.
But instead of just handing a dry spreadsheet to the city council, they present the data through a community event, a visual display, or even a parade. The teacher acts as what the research calls an ignorant schoolmaster.
Meaning they step down from the podium and actually learn alongside the community rather than talking down to them. But doesn't that just invite chaos into the classroom? Do we just toss the curriculum out the window?
Not at all. It's not about abandoning expertise. The researchers use a great metaphor to explain it. Jazz improvisation. They call it prepared spontaneity.
Oh, I like that.
Right. A jazz musician still needs to know their scales and music theory perfectly, but they use that deep foundational knowledge to react to the room, to play off the other musicians, and to adapt to the moment.
So the teacher is the jazz musician, taking the raw scales of mathematics and helping the students improvise with them in the real world.
Exactly. It's about teaching cultural pattern recognition. When a student sees a statistic on the news or a targeted political ad, they shouldn't just obedience test it. They need the tools to ask, what are the underlying assumptions here? Who built this mathematical model, and who does it serve? You are empowering them to actively question their environment rather than just obediently solving for X.
That sounds incredibly empowering for an adult or a teenager. But let's talk practically about younger kids. Can children actually handle this kind of fluid, real-world, improvisational approach to math?
Oh, absolutely, yes.
Or do they need the rigid structures to start? The research points out that kids are far more capable than we give them credit for, as long as we tap into their fundamental understanding before we bury them in jargon.
The study by researchers Squikla and Vonk on how young minds process fractions is so illuminating here. They looked at pre-K children, kids as young as 3 to 6 years old.
It's funny, we treat fractions like this terrifying, insurmountable hurdle in middle school, but these researchers found that 3-year-olds already intuitively grasp them.
Because they tested them using fair sharing tasks. If you hand a 3-year-old a plate of cookies and tell them to share it equally with 3 friends, they will intuitively execute fraction division to make sure nobody gets cheated.
That is so true.
They physically divide a whole into equal parts perfectly well. The math is already there in their heads. It's the scary vocabulary of numerators and denominators that triggers the anxiety later on.
Which perfectly sets up researcher Eric Whitman's argument for a spiral curriculum. Instead of jumping from one outside educational fad to the next, we should base math education on fundamental ideas that children can touch and feel, and just let those ideas spiral upward in complexity as they grow.
Let's walk through one of the best examples of this, arithmegons.
It sounds like a geometric dinosaur, but it's actually a really simple puzzle. Picture a triangle. On each of the 3 corners, there's an empty box. And on each of the 3 sides connecting those corners, there's another empty box. The rule of the game is that the number in the box on the side must equal the sum of the numbers in the 2 corner boxes it connects.
Precisely. So if the corner boxes have a 2 and a 3, the box in the side connecting them is a 5. Now, in first grade, you can give children physical tokens or counters. You give them a few numbers on the triangle and let them figure out the missing ones through trial and error.
Right.
They are physically playing with addition and discovering patterns.
But the beauty is how it spirals. By the time those exact same kids are in high school, you can hand them that exact same arithmegon shape, but this time you only give them the outer side numbers and ask them to find the hidden corner numbers. Suddenly, they are using this childhood puzzle to solve complex systems of linear equations and matrices. The structure remains exactly the same, only the depth changes. Because the shape is familiar, the fear of the abstract math is gone.
It removes the intimidation factor entirely. And we see this again with conic sections. The renowned Italian educator Emma Castelnuovo had a brilliant method for teaching geometry. Instead of writing the terrifying algebraic formula for a parabola on the chalkboard, she would give her students rulers and tracing paper.
This blew my mind. You draw a single dot on the paper. That's your focus. Then, you take the straight bottom edge of the tracing paper, fold it up so it touches the dot, and make a crease. You move the edge slightly, fold it up to the dot again, and crease it.
Right.
You do this 50 times. And because each fold perfectly creates a perpendicular bisector, when you unfold the paper, all those overlapping creases magically outline a perfect sweeping parabola. You can feel the geometry emerging in your hands.
It is a highly tactile, operative way of understanding math. You aren't just memorizing a shape, you are physically constructing the rules that govern it.
And the spiral continues all the way to astrophysics. That exact physical construction method bridges directly into advanced physics. Richard Feynman famously gave a lost lecture where he proved why planetary orbits are ellipses around the sun.
Oh, wow.
And he didn't use massive supercomputers or calculus. He used the exact same simple physical geometric concepts, tracing the envelope of a curve that Castelnuovo was teaching with tracing paper. Starting with physical, intuitive tasks completely removes the math anxiety that usually hits kids in middle school when everything suddenly becomes letters and abstract rules.
When you synthesize all of these sources, you realize we are looking at a profound paradigm shift. Math is not a dead, culture-free language locked away in a textbook. It is a living, breathing, adaptive human activity. It is the French vine pruner calculating the balance of a living plant. It is the Inca artisan weaving positional arithmetic into an abacus. It is the 3-year-old intuitively ensuring everyone gets a fair share of snacks, and the community organizer using data to advocate for their neighborhood.
Which brings all of this right back to you listening right now. In a world characterized by massive information overload and rapid, confusing global shifts, you do not need to feel intimidated by the abstract, rigid math you might remember failing in high school.
No, not at all.
You just need to recognize the mathematical patterns, the spatial reasoning, and the dynamic problem-solving skills that you already use every single day in your own life and work. You're already doing the math.
Because knowledge is most valuable when it is understood and applied in your specific context. True competence isn't about passing a standardized test. It is about how you adapt your mental schemas to the messy, unpredictable reality right in front of you.
So we want to leave you with a thought to mull over long after this deep dive ends. If mathematical thinking is truly just a formalized version of everyday human problem solving, what personal ethnomathematics or intuitive mental schemas have you developed in your own daily work, your hobbies, or your life that no textbook has ever captured?
It is a fascinating question to explore on your own.
Keep looking for the math in the real world. We'll catch you next time.